let's move on from precipitation reactions to acid-base type reactions. We're going to be looking at a very specific type of acid and base reactions here, in that we are only going to be looking at acids and bases that are strong acids and bases. For now, we don't really need to worry too much about those definitions. If you take General Chemistry 2, you'll learn more about that. But for our purposes now, all you need to know is that there are certain kinds of acids, and we're only looking at one kind of acid here. But it is the kind that most people think of when they think of acids and bases. So what acids do is they ionize to produce H+ in water, and bases ionize to produce OH- in water. So essentially, if you put an acid into water, you're going to make H+, and if you put a base into water, you're going to make OH-. The more technical names for these would be hydronium ion and hydroxide ion. Now, acids and bases can have more than one of each of these things produced. As you can see here, we had one H+ produced, and here we had two OH- produced. If they do produce more than one, we have special names for those. So something, an acid, for example, that produces one H+, we consider that to be monoprotic. If it produces two, we consider that to be diprotic. And then if there's more than two possible H+ or OH-, then that would be polyprotic. So it's very similar to what we had with the Greek prefixes before. Mono is 1, di is 2, but then we don't continue on from that. It's just if there's more than two, then it's just poly. And there are very few, for example, acids that could give you more than two H+. They exist, but they're pretty rare. And so rather than giving each one of those different numbers from that point forward their own name, we just say, if it's more than two, it's poly. So a monoprotic acid produces one H+, a diprotic acid produces two, and a poly would just be anything greater than that. When acids and bases react, and again specifically this type of acid and base, a strong acid with a strong base, when they react together, what ends up happening is that the acid and base undergo what we call a neutralization reaction. They neutralize each other. So the acid is very acidic, the base is very basic. They are on opposite sides of this scale, and so when you put them together, they're going to neutralize each other to make a salt. In this particular case, they actually make table salt, but that's not always going to be the case. But they will make some kind of ionic salt and water. Because if you notice here, H+, which is what the acid makes in solution, and OH-, which is what the base makes in solution, when you put those together, you get water. So this neutralization reaction is actually producing water, and then the salt is essentially just whatever's left over. So we had the chloride from the acid, and we had the sodium from the base, and that's just what we had left over. And so that is the salt. So for this kind of reaction, the net ionic equation is always going to be the same. The net ionic equation is it's the way of writing the chemical reaction that only shows the stuff that is changing. So for example, let's see here. Let me erase this stuff. The complete ionic equation for this reaction that's shown here, because there's actually the phases here are left out. This is an aqueous, this is an aqueous, this is an aqueous, and then that is a liquid. So if we were to write the complete ionic equation, which is to say we show everything that is a separated ion in solution as a separated ion, this would be H+, in aqueous phase, plus Cl-, in aqueous phase plus sodium plus in aqueous phase plus OH minus in aqueous phase goes to, sorry for my messy arrow there, sodium plus in aqueous phase plus Cl minus in aqueous phase plus water in liquid phase. Now that's a giant mess. That's a huge equation with ions everywhere and phases everywhere. Complete ionic equations are not usually the way that things are written, but this is again what we call a complete ionic equation. That's what this is. Everything that exists as a separated ion in solution is shown as a separated ion in solution. Now, this is what we just call the molecular equation. And even if you read this molecular equation, you're expected to understand that, yeah, sure, the sodium and the chlorine, excuse me, the sodium and the chlorine are written together, but we understand that they're separated. It's just we're writing them together to make it simpler, essentially. So the net ionic equation is just anything that changes. Anything that stays the same, we just leave out. So for example here in this complete ionic equation, on the left side of the equation we have chloride and sodium in solution, and on the right side we have sodium and chlorine in solution. It doesn't change from one side of the reaction to the other, so they are not going to be included in the net ionic equation because they didn't change. And so the net ionic equation here is just H plus in aqueous phase plus OH minus in aqueous phase goes to water in liquid phase. And that's it. And this is the same net ionic equation for any acid-base reaction between strong acids and bases. Now, it will be slightly different, like I said, for the other types of acids and bases that we're not concerning ourselves with right now. So don't go into someone else's Chem 2 class or someone else's organic class and give this as the answer to all the neutralization reactions. This is only true for strong acid-base neutralizations. But if that's what you have, if you have a strong acid and a strong base neutralizing each other, this will always be the net ionic equation. You just take H plus and OH minus and you make water. Okay, and so you can see that here in this little graphic here. So we have some acid with hydronium ion. By the way, H plus is actually a simplification. It technically is H3O plus, but we're not going to worry about that too much right now. So that's what this here is. That is H plus. We have the OH minus in solution down here. When you mix them together, all you're left with is water and the sodium and chlorine floating around. Alright, so let's write one more equation here. This is asking us to write the molecular and the net ionic equation for the reaction between HI and barium hydroxide. Both of these are strong, by the way. So these are strong acids and bases. And so we can use the rules that we've looked at up to this point for acids and bases. So why don't you go ahead and actually try and give this one a shot on your own, see if you can work this out. So pause the video now and see if you can write both the molecular equation, which is just the normal, so to speak, equation, and then the net ionic equation. Alright, I hope you gave that a shot. We're told we have HI, which would be an aqueous phase, because it tells us that, and barium hydroxide, which is also in aqueous phase. And so what we're going to make on the other side is going to be barium iodide and water. Because remember, any acid-base neutralization is going to make water. One thing you might have noticed here, iodine is a -1 charge. Barium is a +2 charge, so this actually doesn't balance. We actually need 2 iodines to get that to balance, because then we would have -2 and +2. You might have also noticed that the hydrogens didn't balance either. We only had, let's see, we have 3 hydrogens, 2 here and 1 here, so that's 3 hydrogens, and then we have 2 hydrogens here. So to fix that, what we're going to do, and the oxygens also don't balance. If you notice, we have 2 oxygens and only 1 oxygen. So what we're going to do here is, because we need an extra iodine, put a 2 there to get that to balance. That then gives us 4 hydrogens with only 2 over here. And if we put a 2 here to get those hydrogens to balance, that will also balance our oxygens. If you notice here, now we have 2 oxygens and 2 oxygens. And so that is our balanced chemical equation. Put my phase in there. And so then the net ionic equation for this would be 2H plus 2OH minus goes to 2 waters. And I do believe that it is still technically correct to keep the 2's in there. This is one thing I'm actually a little bit fuzzy on, is if you know that the true balanced chemical equation does have 2 of each. I'm not actually 100% sure if then when you simplify it down to the net ionic equation, if you should also simplify the coefficients. That's not something I've seen any rules about, so I'm just going to go ahead and leave those as 2's, since they were 2's up here. But if this was an exam or something like that, I wouldn't count it as incorrect if you put just 1 of each, because that would still be the correct ratio. All right, I hope that made sense. I'm going to leave the video here for now, and next time we will pick up with redox, which is the last kind of reaction we're going to look at before we jump into pizzas, which is really just an analogy we're going to use for stoichiometry. So we'll see you next time with redox.